So I have two videos that taught to place on YouTube, and let me find them very quickly here. And I want to show you one on electrostatic shielding.
Welcome back to the Sierra College Physics Department. Today is a demonstration called Faraday's ice pail with pith balls. On the left we have Faraday's ice pail, which is a wire mesh insulated from an outer wire mesh. We have one lead going to the Van de Graaff generator, another lead going to ground, and there's a pith ball hanging in the middle, one between the two shielding, and one outside. I'm going to turn on the generator.
Note that the inner and outer conductors are connected to the Van de Graaff.
We're getting repulsion on this pith ball, attraction on this pith ball. Now it's going back and forth. And the one directly in the middle is not moving at all. See your instructor for details on how the fields work and how the shielding works. Thank you.
So all the charge stays on the conductor. And so in the middle one, or the inside ball, experiences no field, so it doesn't move. The other two do experience the field due to the charges on the metal, and as a result, you see in one case the one ball goes back and forth. In the other case, the ball just got repelled, and the reason why that one started repelling is because the field was so high on the outer conductor that some charge got transferred to the ball, and so the conductor and the ball ended up getting the same charge. I want to show you another video where you look at the fields due to its sharp point. And so what Tyler did, he set up a Van de Graaff with a hemisphere real close to it so it arcs. And when he brings a sharp object near the Van de Graaff, you see that the Van de Graaff stops arcing to the big sphere.
Welcome back to the Sierra College Physics Department. Today we're going to be doing a demonstration using a Van de Graaff generator and a point. So we have the Van de Graaff generator and a sphere connected to ground, and we also have a point which is connected to ground. So we're producing a spark. And now I'm going to bring the point closer, and we'll see that the spark no longer jumps.
Arcing to the sharp object.
Spark comes back. See your instructor for details on how this works. Thank you.
Okay. So those are two of the items I talked about yesterday. So by the way, if you're interested, we have a Sierra College Physics and Engineering YouTube page, and you can look at a lot of our demos there too. So we're building up this YouTube channel with our demos. Okay, I want to show you another demo. It's related to the properties of charge. So let me switch screens here. Just a second. And I'm going to have to zoom in. Hold on a second. Okay, so what I have here is a device called a Whims machine. And this is another example of properties of charge. I'm actually going to try to bring it a little further away from my computer because it does charge up quite a bit. Okay. Let me see if I can block a little bit more. So we have these two discs that are counter-rotating, and on the back disc, you have a set of brushes, just like you see right here. Hold it up a little bit more. Okay, there's a brush there, there's a brush on the opposite side, and then on the other disc behind here, there's two more brushes. They make contact with the conductors here. There's also some brushes that do not make contact with the disc, and those get charged by induction and transfer the charge to these electrodes. Let me turn the lights on a little bit. And I'm going to do work by spinning those discs. Hopefully you can see an arc. Hopefully you can see an arc here. Or you can hear it. And so you're getting, basically what's happening is you're getting a breakdown in the atmosphere, and so the atmosphere is actually conducting electricity. And if you can see that arc, that's called a corona discharge. Every time you hear that ticking, what happens is the system gets discharged and it builds again. I emailed you a video from MIT which describes how this works. This is just another example of properties of charge. Now, you can't see right now, I'm going to lift this up. There's two canisters below at the bottom. Those two canisters are essentially called capacitors. They're called Leyden jars. And they're used to help store more energy or more charge in the system, really to store more energy. And so what I'm going to do is I'm going to bring this guy down and this guy down. I'm going to charge it to the same voltage, but it's going to take longer because the charge is going to build up in these guys. But then I'm also doing more work. I'm putting more energy into the system. And so when it arcs, you're going to see more energy in the arc. Let's try that. Now you can probably see the spark a lot better. Can you see the arc better? Yeah, this time because there's more energy in it, you can see it better. Now if I make it the gap a little wider, it's going to take longer for it to build. So it's going to take quite a bit longer now. And it's way louder. And of course, because there's more charge, it's much more dangerous. Benjamin Franklin used to play with the Leyden jars, and let's find the story that he got knocked out from playing with them. Okay. And so that arc you see is the corona discharge. And I was going to show you this video later in the lecture, but I think I'm going to show it now. I want to show you another, and this is more of a fun example of a coronal discharge. This is a much bigger coronal discharge that took place at a substation. And this video is online, by the way. So there it is. So you see the people there, and you saw how big that arc was. So again, take a look at those people and compare it to the arc one more time. That's a lot of energy. Okay. So the demo I did with the Whimshurst, once I stored the energy, once I started storing energy in the capacitor, it took longer for the voltage to build up. But once the voltage built up, the capacitor's discharged. I had more energy in the system because I was doing work putting in energy into the system. Okay. Well, just some fun demos for a Monday morning. So what I want to do is I'm going to start the next chapter. I want to start chapter 25. Oops, I got to zoom out. Okay. So I want to start the next chapter. And again, this is a set of abstract topics. Really, most of B&M is abstract. You can't see things a lot of times because you can't see electrons moving. But this sets the stage for everything else that we learn in this course. So these are our topics. And so let me start, let me begin by reminding you of something very similar to gravitation, is that the electric force and the gravitational force, they're 1 over r squared forces, where r is the magnitude of vector. R is the distance between two objects. Okay. So any force that depends on the distance between two objects is called a central force. Whether the r is squared, cubed, or whatever, it's still called a central force. And so if you calculate the work done on an object as it moves between 2 points A and B, the work done will actually be only dependent on the value of the initial point and the final point. That's it. Anytime you're dealing with the central force, that's what happens. You set up that integral. The integral is only going to depend on the endpoints. You saw that with gravity. You'll see the same thing with the electric field. But if I calculate the work done on the electric field, and then integrate the electric field over some path, ds is going to be my element of path. But this force is some function of the distance between the two objects. And this r hat is there because that vector depends on basically the vector that points from one object to the other. Okay, this is the unit vector that goes from one object to the other. So number one, we have f as a function of r, the distance r, and then number two, it's directed from one object to the next. Okay, and so because of that, this integral is going to depend on Your initial point and your final point. Okay. These are called central forces. And the integral only depends on the endpoints. So if you're integrating a closed path, in other words, you go back, if you integrate from A to A, if you integrate around a closed path, the integral is 0. And that's what you learn with gravity. Gravity is a 1 over r squared force. Same thing happens with the electric force. The integral is independent of the path, and so when you integrate around a closed path, the integral you started from, you get 0. Same idea is this. Suppose I take an object and toss it up in the air and then catch it. The work done in that closed path is 0. It doesn't matter what the path is. This marker can take any kind of weird path as it goes from the hand to back. The total work done is 0. And it's the same thing with the electrical force. And as a result, then we can define an electrical potential energy. Just like we did with gravitational potential energy, we can define electrical potential energy. How are we going to do it? We're going to say, well, delta U is minus W. Right? In 205, in the previous course, we said that the work done is minus the change of potential energy. And so what I'm going to say then is, we'll define the change of potential energy as minus the integral from point A to point B, as an object moves from point A to point B, of the electric force dotted dx. And more precisely, you can write the following. It's the integral from point A to point B of Q times the electric field dotted dx. And so this is how we calculate the work done on an object, Q, or test charge Q, as it moves from point A to point B. So suppose I have some source of a field, like some point charge, and I take Q naught and move it between 2 points A and B. The work done on it is given by this equation without the minus sign, and then the change of potential energy is this with the minus sign there. Okay, delta U that's the change in potential energy. So if using the analogy to gravity, if I take this marker and I lift it from this point to this point, the work done by gravity is minus mgh. The change in potential energy is plus mgh. Why is the work done minus mgh? Well, remember the definition of work is the magnitude of the force times the magnitude of the displacement times the cosine of the angle between the two. Well, if I bring this upward and gravity's down, the angle between those two forces is 180. The cosine of 180 is -1. The force is mg, and then this is going to be the height, the change in height. So it's going to be minus mg times the change in height. Of course, the change in potential energy is just going to be mg times the change in height. Okay, so they're opposite of each other. Okay. Questions on that so far? Let me show you a video, and it won't play here, but I have it opened up separately, so give me a second, I'll play the video.
Any electrostatic field is the vector sum of the individual fields created by all the charges in the system. Because a test charge experiences a force wherever it is in the electric field, moving the charge through a field requires work to be done. Recall the general definition of work, and recall the expression for the change in potential energy invested in the field when work is done. In the electrostatic case, the force is the test charge times the electric field. This gives us the expression for the potential energy associated with an electrostatic field.
Okay. Basically summarizing what I've been saying here. Now, we can define something called the potential energy per unit charge. So let me write that down. So instead of looking at the potential energy, we can also look at something called the potential energy per unit charge. Which is basically going to be delta U over V. Let me switch screens here real quick. Okay. We're going to take delta U and divide it by the value of the test charge. I'm going to call this delta V. And we're going to call this the electrical potential. And it is a scalar quantity just like electrical potential energy. We can also say then, because of this relationship, that U over Q naught is V. And V is called the electrical potential. Delta V can be described as the electrical potential difference or the change in electrical potential. And another poorly worded term is the voltage. The units for this is volts. So this is joules per coulomb and superconductor volt. Same volt that is used in analyzing circuits. Okay. So we can talk about instead of the change in electrical potential energy, we can look at the electrical potential difference too. And this is a very useful quantity. And you should do one more degree.
Although the electric field is independent of the test charge that samples it, the electric potential energy is not. However, by dividing the difference in potential energy involved in moving an arbitrary test charge from A to B by the magnitude of the test charge, we get a quantity that is closely related to the potential energy, but that does not depend on the magnitude of the test charge. This quantity is called the electric potential difference. The potential difference provides another way to quantify the electric field and is fundamental to understanding electric circuits.
So let's try to figure out what this means. Okay, let's figure out what a lot of this stuff means that we've talked about so far. I want to go back before I talk about the slide and remind you some things from Physics 205. Again, let me change views. Okay, here we go. If I take an object like this marker and I lift it from this point to this point, I have done work to lift it from here. The work that I've done is mgh. The work done by gravity is minus mgh. So I can say that the work that I do plus the work done by the conservative force, how about that, or the field, equals 0, because in lifting it from here to here, my initial kinetic energy is 0, and my final kinetic energy is 0. So I can say that the work that I have done, what the applied work, plus the work by the field is 0. And that the applied work is minus the work done by the field. But that's just delta U. Okay? Put your head up here. So when I take this marker, which is in my hand right now, and I lift it to some new height up here, the work done on it is minus mgh. The work that I've done is plus mgh. The change in potential energy is plus mgh. So the work that I've done, the work that I put into the system, goes into storing energy. Okay? Yeah, I've not. Gravity's done negative work, right? When I lift this marker, gravity's done negative work. I've done positive. I put energy into the system, right? What's the system? Well, the system is the marker of the Earth. So in lifting this up, I've put energy into the system, consisting of the marker and the Earth. And so now that system has energy stored in it. Does that make sense? Okay, so the same thing applies when we talk about electric fields, right? So this can be the work done by the electric field, and this is the work that's required to move the object between points A and B in the electric field. And so the work that you do to move it between points A and B, such that delta K is 0, is going to be delta U. And then if you divide that by Q naught, then we can describe this thing as the work per unit charge that's required to move a test charge Q naught from point A to point B within the field. In other words, if I put a point charge here, a source that produces a field, and here's my Q naught, if I move it from point A to point B here, okay, the work that I do in moving it from here to the work that I do in moving it from here to here is basically the change in potential energy. The work that I do per unit charge as it moves from here to here is your delta V. Okay? So that's all really I'm saying here. Now, what else can we learn about these ideas? Well, let's assume, to make the math easy, what if the electric field is constant? Let's work out this integral for the case of the electric field is constant. And I'm doing this because it makes the math easier and you can see some things regarding this. So, we're just going to look at the simplest possible case and see what we can learn from the simplest possible case. We're going to take this integral. The work done by the field is going to be Q naught times E dot dx. Okay? And if E is constant, I can write it like this. E, d is the distance we move the object. And write it like that. That's the work done by the field. Okay. So let's say we have an object moving from point A to point B. This distance is d. Whatever path we choose, okay, doesn't matter. This is the distance between the 2 points. Now, to make it a little simpler, let theta be 0. That makes the work done by the field Q naught dB. But this is minus delta U. For U. So delta U is minus Q dB, Q naught. But if you look at this equation up here that I wrote down, if delta U over Q naught is delta V, then delta U is Q naught delta V. So that tells me that minus E times D is delta V. So what does that tell me? Well, if this is positive, that's negative. If this is negative, that's positive. This side's got to be positive. It's saying that these are opposite in signs. What this says is that the electric field is in the direction of decreasing V. That's what it tells me. If this is positive, E is negative. Imagine we're along the x-axis. If V increases in the x direction, E is in the opposite direction. The electric field is in the direction of decreasing V. Okay. Now, of course, that comes from our definition that telling the field is not a special here. Okay, it comes from that. So let's talk about a proton in a field. What can we say about a proton moving in a field? And when you're ever asked a question like this, you should not memorize. You should try to just figure out from your knowledge of physics, because you can make mistakes very easily. So let's say I have a proton. in an electric field. So let me draw an electric field. Let me use green if you like. I want to obscure my picture. So there's an electric field. And then to make the math easier, let's assume that, or to make the idea easier to see, let's make the field uniform. Here's the charge Q, and it says that the charge is moving in the direction of the electric field array. So V is this way. What's going to happen to the charge? Is it going to speed up or slow down? Well, F is Q times Z. Q is positive, so that means the force is in the direction of the electric field. That means it's going to speed up. So proton speeds up. That means its kinetic energy increases. We know that delta U plus delta K equals 0. So delta K is bigger than 0. Well, if this speeds up, this has to go down. Does that all make sense? I mean, if I take this marker and I drop it, what happens to its potential energy as it falls? It decreases. What happens to its kinetic energy? It increases. Same idea. Okay, same idea. But delta U is Q delta V. Remember, delta U so that means that delta V is less than 0. And that makes sense because we said that the electric field, it points in the direction of decreasing V. So the proton, when it moves in the direction of the electric field, it speeds up, the potential energy decreases, and so does the electrical potential. If the proton were moving in the opposite direction, then it would slow down, this would get bigger, and that would get bigger, because it's moving. It would be moving against the direction of the electric field. If it's slowing down, it has to be moving against the direction of the field. Or it was originally moving to the left. Okay. Let's replace the proton with the electron. And let's say the electron is initially moving to the right. What's going to happen to the electron? If the electric field is to the right, which direction is the force? It slows down, right? It'll slow down and then eventually reverse direction. You're correct. Okay, you're right. So this thing will slow down. Let's just focus. Let's not get to the point where it moves to the left. Let's just say it slows down. Okay. If it slows down, then this is less than 0. Then this is to be greater than 0 because of this. But what about delta V? If this is greater than 0, and the charge of the electron is less than 0, this also has to be less than 0 to keep this positive. But it's still the case. Why? Because the electron, at least for the time being, is moving in the direction of the electric field. So as it slows down, the electron is moving in the direction of the electric field. It's moving in the direction of decreasing potential. Once it turns around and goes back the other way, it's going to be moving against the direction of the electric field. And so it's going to be moving in the direction of increasing electrical potential. Does that make sense? It's fun to try all the cases. It's fun to do the proton going to the left in this field. See what happens. But this shows you that the electric field is in the direction of increasing V also. I mean, this thought experiment shows you that the electric field points in the direction of increasing V. Questions on that? Okay. And I'm going through some of this slowly because it can be confusing at times. These questions always confuse me as a student. That's why I kind of spend a little bit of time on it. And you can't try to just memorize the answer. At least you might at the beginning, but if you do it after about a couple months of not thinking about this stuff, using your memory is not good. Using this idea and this idea is what you want to use to answer that question. Okay, that's good. So let's do a simple problem. I want to find the speed of a proton that is accelerated from rest through a potential difference of 120 volts. And then we'll repeat it from the electron. And I'm just going to use this equation. It's a conservation of energy problem. If I accelerate something to a potential difference of 120 volts, it's the same thing as I drop in this object. So I'm going to use this equation to answer this question. Let me rewrite conservation of energy. So we're going to have a proton going through an electrical potential difference, and so its potential energy is going to change. So we want to speed this thing up, right? Q naught delta V plus 1/2 mv final squared minus 1/2 mv initial squared equals 0. It starts from rest, so this guy is 0. Okay, Q naught delta V plus 1/2 mv final squared equals 0. And Q naught delta V because V is positive, right? And this term on the right has to be positive because we have V squared in it. So that means if Q naught is positive, delta V has to be less than 0. So delta V is actually minus 120 volts. All right. You're going from a higher value of V to a lower value of V. I'm going to have minus Q naught times minus 120 volts equals 1/2 and V final squared. Now let me say something about the energy of this thing. The total energy then is going to be the charge of the proton times this number. Hopefully it's not too light on the border. That's the total energy. That's the total kinetic energy it has. Okay? This is the total energy in joules. But I can convert this to electron volts. Okay, one electron volt is 1.6 times 10 to the minus 19 joules. Guess how many electron volts this is? It's 120 electron volts. What do you think we divide by that? We develop that conversion factor. Okay, because it makes this nice. If you accelerate a charge through 120 volts, its energy is 120 electron volts. Okay. In physics, or in atomic physics especially, we use the electron volts because the energy values are so small. Instead of saying, 1.8 times 10 to the minus 17 joules, we'll say 120 electron volts. Okay. I forgot what this comes out to be. Okay, so let's solve for the velocity. This is simple math. I have to use this. I can't do this in electron volts. I got to do it in joule if I want to find the velocity. The mass of the proton so if I do this calculation, I think this comes up to 150,000 meters per second. That's how fast it's going. Yes, it's 150,000 meters per second. That's fast. It's not even close to the speed of light, but it's fast. Okay. The speed of light is 3 times 10 to the 8th. So C oh wait, I wrote a big one. It's 3 times 10 to the 8th meters per second. So it's not even 1% of the speed of light. Now what if it were an electron? What if it was an electron? Then what? Or if this was an electron, I'll use red, Q is positive. I'm sorry, Q is negative for the electron, so it's going to cancel this minus sign. And this has to be positive. So if this was an electron, the electron has to go from a lower V to a higher V. A lower electrical potential to a higher electrical potential for this to work out. But still, its energy would end up being 120 electron volts. What changes is this denominator. And it moves much faster. Let me calculate it. It comes about 6.4. That's 10 to the 6 meters per second. Now you're within 2% of the speed of light. So now you start thinking, okay, I got to consider relativistic effects. Okay, so really I should take into account relativity in doing the case for the electron. Well, actually it's only 2% of the speed of light, so you're still at the fringes. Okay. If you take into account relativistic effects, this might change by maybe a couple percent. Okay. And we'll do this later on in the semester. Well, let's take a look at the electrical potential due to a point charge. I'm going to calculate the electrical potential due to a point charge. Can we derive an equation for this? Of course we can. Okay. So I got to consider the idea of the electrical potential, which is this. The electrical potential difference, sorry. I need to use that idea. And I need to use the equation for the electric field due to a point charge. I'm going to get V due to a point charge by integrating the electric field over a path. I'm going to use this definition for delta V to get the electrical potential due to a point charge. That's my goal here. When I take an integral of the I'm going to take this guy, I'm going to take minus this delta V. In other words, here's a source. You now want to move from point A to point B. I want to find delta V as you go from point A to point B because of this source. And remember, R hat is a unit vector that goes from B to the source, or A to the source. If I do this integral, there's a dot product here. And you can easily see that the only contribution, the only non-zero contribution comes from ds vectors, ds components that are along R hat. If you have components of ds that are perpendicular to R hat, they will not contribute to the integral. As a result, I can rewrite this integral in the following manner. And I'll go from R sub A to R sub B. And that'll give me my delta V. Well, gosh, this is not a hard integral because you all know how to integrate 1 over R squared. And so, what are we going to get? We're going to get K times Q times 1 over R sub B minus 1 over R sub A. The minus sign disappears because when you integrate this, you get a minus sign that cancels out this way. And so this is going to be V at point B minus V at point A is equal to K times Q but that's the electrical potential difference between point A and B. Now, one of the things about electrical potential that's common with the idea of potential energy is that these things are defined within a constant. So I can define where my zero is. So I'm going to define my zero in the following manner. I'm going to say V equals 0 at R equals infinity. And I'm going to let R sub A equals infinity. If I do that, then this term is 0 and that term is 0. And that says V sub B is K, Q, R sub B. Let's write it in general and say V is K, Q over R. This is the equation for the electrical potential due to a point charge. So here's a source of the field. The electrical potential at any location is given by this equation. The fact that this V changes means you have an electric field. Okay, the fact that V changes automatically tells you there's an electric field. It's a scalar. It's very easy to calculate electrical potentials. There's the scalar. You just add up a bunch of numbers. They're positive or negative. There's no components. Right? There's no components of this thing. Now, R here, and it's probably not going to be important in this course, but you should understand that R is the magnitude of the vector that points from the source of the potential to the point at which it's measured. Okay, there are certain cases where the knowledge of this is important. Okay. Or you might end up with a sign error in doing the calculations. So if I want to find the electric potential due to some sort of discrete charge distribution, all I got to do is add the electrical potentials at point A that you see in the figure due to each one of those charges. So in that picture you see you're going to have the sum of 3 terms for Q1, Q2, and Q3. In that picture that you see, the total electrical potential at point A is K Q1 over R1 plus K Q2 over R2 plus K Q3 over R3. That's it. Linear superposition. It's a very easy calculation. Now, but I want to ask a little bit of a more challenging question. Suppose you have two charges, Q1 and Q2. What is the work that's required to bring Q2 from infinity to a distance R12 from Q1? Where's Q1? In fact, I can ask the following. How much work is required? This is going to be the same answer. To assemble those two charges. I want to get the same answer to both questions. But I can ask both questions. I'm going to assume that these two charges are isolated from the rest of the universe. So I put a charge Q1 here. I brought it out from way far away at infinity. I put it there. How much work is required? Well, if that's the only thing around, delta V is 0. That means delta U is 0. So it requires no work to put this charge here. Because, remember, we're talking about an isolated system. Now I got to take the second charge, bring it from infinity to here, Q2. So this came from infinity. And this distance is R12. I want to know how much work it takes to bring this guy from infinity to this point. Remember what we said is the work that I do is delta U, which is Q delta V. Well, this is going to be Q2 delta V. This is going to be equal to Q2 times V evaluated R12 minus V at infinity. Well, what's V at infinity? 0. And so this is going to be Q2 times K Q1 over R12. Number one, that is how much energy it takes to bring this guy from infinity to here. But it's also the amount of energy that's required to assemble this whole system of charges, because to move this guy here requires more energy. And so this is delta U, and this is U final minus U initial. And so this ends up being the energy stored. That's the energy stored between those two charges. That's the energy stored between those two charges. Okay. This is the electrical potential energy equation for two charges. Okay. The amount of energy stored in the system. You okay with that? What about if I want to assemble the system of three charges? What do I do now? I want to know how much work is required to assemble this. Yes, that's for specifically for a 2-point particle system. What if I do 3 points? Well, I don't want to redraw everything, so let me draw my third point, and it doesn't matter what the geometry is. So I'm going to put the third point right there. This is R13. Oops, it's not there. R23. I know already how much work it takes to assemble the first two, this. Now I got to take a third one and put it here. So all I got to do is figure out how much work it takes to put this one here and add it to this guy, and it tells me the total amount of energy is required to put this thing together. So the work required to bring the third charge in is going to be Q3 times delta V1 plus Q3 times delta V2, because both of them are producing, each one of these charges produces delta V. Well, remember that one of these has a, Q3 was at infinity, so the initial term is going to be 0. V1 initial is infinity, V2 initial is going to be infinity. And so what I'm going to have is Q3 times K Q1 R13 plus Q3 is K Q2 over R23. By the way, it turns out that this is the potential energy for charge number 3, but I'm asking for the energy required to assemble the entire system of charges. So I got to take this and add it to that. So the total energy to assemble a system the amount of work I have to do to assemble it is going to be this. And this is the energy stored in the system. This is view of the system. Not only is this the work required to assemble the system of charges, this is the energy stored in the system, because again, we said that W applied is delta U. And this top term here is the potential energy just for Q3. This is the potential energy for the whole system. Now, if this number ends up being negative, okay, if this number is negative, this implies that you can have a system that's stable. You can have a system that wants to stay together. Because if this is negative, what happens is I'm doing negative work to assemble it. I have to do work to keep this from speeding up into Q1. So typically when you do this, it says you have a stable system. When people try to study whether an atom can be stable or not, let's say I have a hydrogen atom, and I want to see what happens when I add 2 electrons to it. And I look at the potential energy of the system, it's more complicated in this calculation. If I get a positive number, it's going to tell me, oh, the atom is not going to accept the 2 electrons. But if I get a negative answer, it's going to say, oh, the atom will accept the 2 electrons. So it's actually an interesting calculation. It tells you whether a system can be stable or not. Okay. Questions on this? If I were to introduce a 4th charge, I would end up adding 3 more terms, because bringing in the 4th charge, I'd have to do work against this guy this guy, and that guy. So it adds 3 more terms. And you can write a general equation for this, for point charges. You can write it as a summation over the i's and j's. Why is there 1/2 there? I mean, if you're writing a computer program to do this, you would write it like that. You'd write an equation like that. So why is there a 1/2 if you sum over both I and j? Well, if you sum over I and j, and if you do that summation blindly, you're going to get k, q1, q2 over r12. You'll also get a term. Yeah, each pair is counted twice. Right. K, q1, q2 over r12 is the same thing as k, q2, q1 over r21. So you're counting everything twice, so you got to put a 1/2 there. Okay. So we're learning a lot out of this. So the next thing is we're getting a lot of information out of this delta V. We're going to get even more. This thing is a powerful idea. I can obtain the electric field from delta V. So I'm going to use this expression here. And I will show you this. If I avoid doing integration, if I do not integrate, this ends up being dV equals minus E dot dS, which is minus E sub x dx. Okay, I'm only doing this for a rectangular coordinate system. In Calc 3, you'll probably do this for a more general coordinate system, but I'm going to do it this way. That's how you would write dV. Now, if this were a one-dimensional problem, then you say dV is minus E sub x dx. Well, then it's obvious then that E sub x is minus dV over dx. For any one-dimensional problem, isn't it true I can write E sub y is dV over dy, and E sub z is dV over dz? Isn't that true? So these are derivatives. So I can write it this way. Because of this, I can say dV is minus the derivative of v with respect to x, assuming y and z are constant. I'm going to run out of space. Hold on, let me rewrite this real quick. If I do this in 3D, I can write it the following way. Those of you who had Calc 3, you know what I'm doing now, right? I can write it like this. Well, in Calc 3, to avoid writing the fact that we're taking the derivative assuming y and z are constant and x and z are constant, x and y are constant, we write it like this in Calc 3. We change the symbols. And so there's a shorthand notation for writing this. In fact, there's a shorthand notation for writing this. I can write it like this. And so the electric field then, the vector, is called the gradient of the electrical potential, or minus the gradient of the electrical potential. The method of steepest descent. And I'm going to give you Calc 3 to remember that. The electric field is minus the derivative of the electrical potential. Okay, the electric field is minus the derivative of the electrical potential. So if you're one-dimensional, if you're living in a one-dimensional world, then you just have this term. It's minus the derivative of the potential. So let's do a simple example. You're given V, I'll try to hurry the last few minutes. If you're given that V, how do you find the electric field? And don't worry, we're not going to spend a lot of time doing complicated Calc 3 derivatives. They're all going to be pretty simple. So, what does it say? I want to find the electric field. I'm going to take the negative of the derivative of this function with respect to x. The only thing with an x in it is this guy. I want to take the negative of the derivative with respect to x. If I take the derivative of this term with respect to x, I get 3,000. And then I got to multiply by -1 because of that. Then I take the derivative of this respect to y. Well, look, there's no terms with y in here. I'm putting in that just for fun, but really, I don't need to put the 0 in there. And then I take the derivative of this thing with respect to z. Well, I'm going to take the derivative with respect to z. The derivative of z squared is 2z. 2 times 1,500 is 3,000. I got to put in a minus sign. I get. This is a vector, so this is the x component. And this is the y component. The one thing I forgot to do is that the electric field is this. I was hurrying, sorry about that. That's the electric field. This is equal to minus the gradient. That's the Bell operator. Okay? That's it, that's all we do. Now, one of the things this tells you is the following. V is in volts, that's the distance, and this is the electric field. This is a voltage divided by a distance. So the electric field can also be written in volts per meter. So we can write this in volts per meter. Okay, we can write this in volts per meter. Where did the Px and Pz go? Well, you mean here? Well, I'm calculating E, right? This is ds. I'm sorry, this is dV. I want E. So E is right here. There's no dx and there's no dz. Okay. So I messed up because I was in a hurry. I didn't write this down. Okay. Sorry about that. But I'm running at the end. I want to talk about equipotentials real quick, and then I'll be done. And I got to run to my next class. Okay. So anyway, these calculations are straightforward. There's like maybe one in the homocron rate for these calculations. Basically, it's the electric field is a derivative of the electrical potential. Because most of the problems we do in this course are one-dimensional problems. The electric field is minus the derivative of the electrical potential. In 3D, the electric field is minus the gradient of the electrical potential. What if this is 0? What if dV is 0? Well, two things. One, if it means E is 0. It means the electrical potential doesn't change. So it can either mean or the electric field is perpendicular to ds. But the dot product is 0. It means your path is perpendicular to the electric field. So if your path is perpendicular to the electric field, V doesn't change. Okay? Any path that you take where V doesn't change is called an electrical potential. So either E is perpendicular to ds, or E is 0. That means no work is required to move the charge along a path where this dot product is 0. Those are called equipotentials. Now in 3D, they're called surfaces. Okay, in 3D, they're called surfaces. Uh-oh. I'm having a connection issue.
This meeting is being recorded.
I know I lost a bunch of you guys for a second. Okay, now we're back. Sorry. So you're going to see 2 videos on Zoom. My connection's unstable. My video's not, though. So, the electric field lines are always perpendicular to electric potential surfaces, equipotential surfaces, since E is perpendicular to ds. And the surface of a conductor is always an equipotential. And the reason why is because the electric fields are always perpendicular to the surface of a conductor. And so, the surface then forms an equipotential. The entire surface of a conductor is at the same B. Okay, I think I better stop here because we're all having trouble with the connection. Okay, and I got to go to my next slide. I'll finish the discussion on equipotentials, and then I'll talk about how to calculate the electrical potential for various charge distributions. I hope you guys are still there. Okay, I'll finish my equipotential discussion on Wednesday at the beginning. All right, so the video you're going to see on Converse Zoom, there's going to be 2 because it stopped and started again. But you'll have one on YouTube for this lecture. Okay? All right, we'll have a good day. Thank you.